Good evening, everyone. We are in the week 12 of the course Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. This is the last week, and this is about implementation of multimode digital control and course summary. Let me share my screen. I hope you are able to see my screen. Can anyone please confirm? Yeah. Yes, sir. Okay. So let me start. So this is the final week of this course, which is implementation of multimode digital control as well as course summary. So this course summary part, we'll discuss later. So as there is a additional session where we'll be discussing the course summary, I have not put any slides related to the summary of the course. So in this session, we'll only be discussing about the implementation of multimode digital control as well as by frequency DPWM that Sir has covered in this week. So this course summary, we'll be discussing this on 18th October. So please note it. So 18th October, and this is Wednesday. And the time is 6 p.m. to 8 p.m. So the link will be the same in the same Zoom meeting link. Sorry, 6 p.m. to 7 p.m. This is only 1 hour session. So we'll quickly summarize everything that we have discussed. So sorry, this is 1 hour session. So it will be from 6 p.m. to 8 p.m. And I have informed the NPTEL time regarding the date as well as time. So they'll be informing you soon. I have not gotten any confirmation from them, but I have submitted the details. Okay, so before we go into the week 12, let us just summarize what we had discussed in the last week, which is the week 11. And the week 11 is about design and validation case study using digital voltage mode control and mixed current mode control. So we have seen again, there was a quick recap of the implementation of digital voltage mode control and mixed signal current mode control. And we have seen the Verilog implementation, not the HDL code, but the block diagram. And then we have seen the MATLAB simulation versus hardware results comparison, a quick comparison of how well the models that we had developed are matching with the hardware. And it will never be exactly matching, but still there will be some unmodeled dynamics, some parasitic mismatch, and the tolerance of the inductor. So there will be some mismatch, and it is expected. And we have seen that it is at least giving some direction in which the hardware is working, so we can get an estimate of the working of our control before going into the hardware implementation. So this will make sure that yes, our logic is correct and there is no issue. And if there is an issue, we have to resolve it in the simulation before going into hardware, else it may damage some key components. And production is there will, of course, there will be production, but it is safe to do and check whether the controller is working in the simulation before going to the hardware. And then we had seen the design case study as well. So in DVMC, we have seen two designs. One is pole zero cancellation and alternative method. And in current mode control, we had seen load current feed forward and load current, without feed forward and with feed forward. So this is the summary. Sorry, this is again week 11. I'll modify in the final slide. So in the week 11, first, as I have mentioned, we had discussed about the digital voltage mode control. First, there was a quick recap of the implementation and the blocks, and then we have compared simulation versus hardware results, and we have seen multiple case studies of the hardware results, and we have seen how closely it is matching with the simulation. Then we have discussed about the design aspects, mainly the two design techniques. One is the pole zero cancellation, and the other one is the alternative method. And we had seen what are the differences and how alternative method was able to improve the voltage transient response. And we have seen some comparative case study of the simulation results of method 1 versus method 2, and what are the major improvements or major differences in these two methods. And in the mixed signal current mode control, again, we had done a quick recap of mixed signal current mode control, and this peak or could be valid, but we are only talking about peak current mode control because of duty ratio is less than 0.5, and for duty ratio less than 0.5, valley current mode control will be unstable. So that's why we are going for peak current mode control. And similarly, we had discussed two design case studies, and one is with load current feed forward and one is without load current feed forward. And yeah, someone has asked one question to sir, like how this load current feed forward is improving, and also sir has discussed in his lectures how it will improve the output impedance, and how it is shaping the output impedance, and how it can improve the shaping output impedance, and how it can improve the output voltage undershoot as well as overshoot during transient. And we have seen that there is no significant undershoot or overshoot during low transient, even if it is small load step or even if it is high load step, because the output impedance is almost zero, or I would say negligible, not exactly zero, because of which the undershoot is also negligible. And we had seen comparative study of how much the undershoot and overshoot reduction is possible using load current feed forward compared to without load current feed forward. And then we had quickly discussed about some topic called multimode, and which is again a very crucial topic. So the last time we had only some brief introduction to PWM as well as PSM. And we have seen why do we need PWM and PSM, mainly because of the efficiency at light load conditions. So efficiency at light load conditions. But this was just an introductory slide. But today we will be discussing about the Verilog implementation. Okay, let me just take it. A Verilog implementation of the same, and we'll also discuss about other multimode control architectures. And then last week we had solved from few problems, 2 to 3 problems, and this week also it will be more of conceptual and followed by few problems solving. So week 12 is about implementation of multimode digital control and course summary. So in the multimode, we will be discussing today two multimodes. One is the PWM and PSM. The introduction of this has been discussed in the last week session, which is week 11, and the other one will be PWM PFM. And as I have discussed course summary, I will not be covering in this session, but it will be covered on the Wednesday session, which is day after tomorrow, 6 p.m. to 7 p.m. So the week 12 outline is as shown. In the lectures, sir has first covered bi-frequency spread spectrum, but as we had discussed PWM PSM in the last session, I thought we'll first discuss the multimode digital control, complete it, and then we can dive into bi-frequency spread spectrum as it will be continuous. So I have just put it at the third position after the multimode digital control, but we can quickly revise and see the advantages of PWM as well as PSM, how it will improve the efficiency, all those things, and how to implement it. So first, again, as we had done in the earlier sessions also, first we'll go to the top-down design methodology, that block diagram, and then we'll see what internal blocks are to be implemented, how is it different from the previous control techniques, and what additional blocks are needed. And we'll only be discussing about the additional blocks because other blocks are already discussed in the previous session. So we'll see the Verilog HDL implementation followed by a few hardware results. So how PSM to PWM that mode is changing when there is a low transient, and how it will affect the voltage undershoot, as well as some different case studies we can check. And then we'll check the PWM PFM. So this is another multimode digital control that is widely used in many products, which sir has also shown in lecture 118. Some commercial products are has shown and what are the control architectures that they are using. And many of the commercial products, they'll use light load control architectures, and then when the current increases, it will move into some other control technique. So again, here we'll discuss the top-down design methodology followed by Verilog HDL, only the blocks that are new and that are not discussed in the previous session, and then followed by a few hardware results. And then we will discuss about bi-frequency spread spectrum, what is the need of bi-frequency spread spectrum, what are its impacts on the transient response, as well as that FFT that we had shown in the previous sessions also. So again, we'll discuss about top-down design methodology. And here, Verilog HDL implementation, there is no significant change in the HDL code compared to the voltage mode control, the DPWM block. So we'll just quickly see what will be the differences, and then followed by hardware results and the power spectral density, that FFT that we had shown. We'll also see how it will affect that bifrequency spread spectrum, affect that FFT, and followed by two problems. And yeah, so this week is quite simple, only two multi-mode control architectures followed by bifrequency spread spectrum. And then Sir has summarized the course in 4 lectures, but we'll do that in the Wednesday slot. So coming to our today's topic, yes.
Sir, I'm clear with the pulse skip modulation, but I'm having a little bit confusion about the pulse frequency modulation. How it is different from PWM, sir?
Okay, like, should I explain now or should I explain when we go into PWM PFM?
When we get into there, you can explain.
Okay. Just remind me, I'll also explain. So when we talk about PWM PSM, as you know, PSM, like, it is a fixed duty ratio. So this duty ratio is fixed as well as this time period is fixed, but it will have two things. One is the skip pulse, other one is the charge pulse. So one is skip pulse, charge pulse. So skip pulse means when the V naught is greater than V reference. So if V naught is greater than V reference, then it will skip because V naught is already more than V reference. And if V naught is less than V reference, then it means it has to be charged so that V naught crosses V reference and it will charge. So again, this is a DCM operation, which means the inductor current becomes 0 before the end of the switching cycle. So it will become 0 and stay at 0 until the next charge pulse come. So yeah, we'll first discuss about the top-down design methodology, the Verilog HDL, followed by the hardware results. So just let me quickly summarize what we have discussed about PWM and PSM. So in PWM and like PSM, both are voltage mode. So the first multi-mode control, digital control architecture that we'll be discussing is the voltage-based multi-mode digital control architecture, and the second one, which is PWM PFM, is current mode control based architecture. So here, as we know, in the voltage mode control, we have the feedback followed by the analog to digital converter, giving the V naught in digital subtracted from the reference, which will generate the error voltage fed to this PID controller block, giving the control voltage. And then this is the DPWM, counter based DPWM, compared with the ramp, which is a counter. So this will give us a reset pulse, and set pulse is switching frequency because it is fixed frequency control. And then this will go into the dead time block. We have given 60 nanosecond dead time, and then that is going to the high side switch as well as low side switch. And when we come into the digital PSM, as we have discussed, so it completely depends upon whether V naught is more than V reference or less than V reference. So we'll check whether this feedback digital is more than V reference or less than V reference, and then it is passed through a D flip-flop because it will only be checked after the completion of the cycle. It will not immediately update. So it should store that value and it should be reflected until the next switching clock comes. So we are using a D flip-flop because it works with the logic that we want it to be working here. And the output is QPSM, PSM logic, and this is the QPWM. This is the PWM block, and then they're set to the AND gate. So if it is charged, then it becomes 1, and then it becomes QPWM for charge, which means it has to be charged, so the gate pulse will go. And if it is skip pulse, then it will be 0, and the output will be 0. So it will be 0 until the V naught comes below V reference, and then it will charge again. So this is the basic architecture or the working of digital PSM in buck converter. Now coming to the multi-mode. So when we say multi-mode, it has more than one mode. Here we are considering 2 modes of operation. One is for light load, one is for like current higher than what we consider as light load. So these light load and below which below what value of current it has to be changed, that comes from the efficiency curve. So the efficiency point at which like, let me use a different color. So when we draw an efficiency plot and say this is PWM, and say something PSM is like coming like this, then what we wanted to do is we would like to have this efficiency curve. So below this I naught, it should work in PSM, and above it, it should work in PWM. And that is the basic thing, because the efficiency is the main target for majority of the products. So from there we are getting multi-mode. So it has to be 2 modes, so that in the light load condition it is operating in PSM, and in the full load higher load condition it is operating in PWM. So this is again the multi-mode block, similar to the voltage mode control, ADC data 10-bit, and transient to give the reference transient or load transient, and main clock 100 megahertz clock, followed by PWM high, PWM low, and Q load going to the resistor, which will increase the like a load step of transient. And so if you go into the inside, it has 2 modes. One is the digital voltage mode control, mode 1, and the digital PSM, mode 2. So if we talk about this implementation, which again we have discussed in the week 11 last session. So as if it has 2 blocks, one is the digital VMC and other one is the digital PSM. But when you come to the output side, each of the modes are generating one high side, one low side. So this is generating one high side thing, one low side thing, and here also it is generating one high side thing, and here low side is always 0 because it is DCM. Low side switch is always off. Either the high side will be on and then the low side will be off, so the diode will be conducting. So here it is again generating one high side. So now how will we know whether this should be passed or this should be passed? So for that there is a bit which is PWM PSM. So this will be like a mode detection, we can say. You are able to hear me, right? Hello.
Yes, sir.
Okay. Okay.
Yes, yes.
So here also we have mode detection. So when we say like PWM PSM, that is a bit, single bit. So if it is 1, so I can say if say there is a bit by the name PWM PSM, and it can have 2 values. One is 1, other one is 0. When it is 1, it means it is operating in PSM, and the PSM Q high temp will be sent to the PWM high, and the other one is always 0, so 0 will be sent to PWM. And when it is 0, it is operating in PWM. So the QH time coming from the PWM will go into the PWM high, and here QL temp that is going that is coming from the digital VMC block will go to PWM low. So like this can be implemented. So we can club digital VMC block Verilog code and digital PSM Verilog code. But if we
Sir, I
actually
have a doubt.
yeah.
Sir, like the mode change will be detected by itself, or we have to give it forcefully, sir?
Yeah, we have to tell the code when it has to change. So basically it
How,
comes from the I
how
naught.
that point, sir,
This I naught.
like, okay, how we gonna calculate this I naught, sir?
So that will come from the efficiency. So whenever you have designed the buck converter, you know the losses models, right? What losses, conduction losses, switching losses, driver losses, capacitance, output capacitance losses, inductor losses, DCR losses, ESR losses. So when you
Yes.
calculate all the losses and then when you plot it, so this is the efficiency, and across I naught, you will get this efficiency curve. So when you do that for PWM and when you do that for PSM, you can get an estimate of I naught, below which PSM has higher efficiency than PWM. So you have to detect this I naught and then accordingly shift the PSM. So whenever like you say any commercial product, so they should somehow get that I naught information, and then they'll check whether it is above I naught, say I naught dash they got. So they'll check whether it is less than or more than I naught, and accordingly they'll set that bit to either 1 or 0. But in our case, we had not done that. So we have only directly given light load as well as full load. So we are by default giving in that code. But when you go to commercial product, there should be some sensing so that it will be fed back to the controller and it will take the action accordingly.
Okay, sir.
So yeah, where are we? So that is happening. But if you see, like we can take 2 codes that we have already discussed, but it will increase the like the resources, because if you see here there is one modular encounter and here there is one DPWM. and here it is being compared with the ncon, and it is giving reset pulse. So here also it is having a fixed ncon, and there is a counter. So what we can do is we can use a single block can be used, right, to reduce the cost, or when we say cost, like the number of resources that are being used in FPGA, or if you go to ASIC, so we can use a single counter, so that it again it can be either PWM or PSM. So both will not be working at a time. So either it will work for PWM or it will work for PSM. So we can use a single DPWM block. A single DPWM block can be used. So the Verilog implementation is as follows. It again has a main module. So Sarah has discussed in detail, but I will not be discussing that much detail as we have less amount of time. Also, majority of the blocks are similar to what we had regressively discussed in the earlier session. So I will not be touching these three. So the main module is the multimode DPWM DPSM, and it has the 100 megahertz clock, one clock for going to ADC, and DAC we are not using because it is voltage based. So DAC is not there. These are the PWM high and PWM low. So this is the final QH as well as QL, and ADC data is the V0 data that is coming from the ADC, and the Q load is for the load transient. And Sar has set one OP multimode, whether it has to be multimode or not. So Sar has put a bit. So if this like a say switch, that switch if I keep it 1, then it will operate in multimode, like it operated PSM in the light load. If I make it 0, then it will operate throughout PWM. So again, it is like PWM or PSM or only PWM. So there is an external provision of switch. So using that switch, I can tell the controller that whether I would like to operate in PWM PSM or only PWM at light load condition also. That is one provision that we can keep, but when you go to commercial product, there might not be such scenario, because they are including PSM for efficiency, so they might or might not give that additional flexibility to operate in either PWM PSM or PWM. So it again depends upon the manufacturer. So then there are the input and output port declaration, followed by registers, wires, and parameter declaration, followed by the module instantiation. So in module instantiation, first we have clock generator, similar to voltage mode control, followed by digital PID controller, followed by counter-based DPWM. Then there is this mode selection, which is the unknown block, which we had not discussed previously. So we'll again discuss thoroughly today. So clock generator, digital PID controller, and counter-based DPWM, these are all discussed previously, so I'm not touching upon. So after the module instantiation, there are few lines of code, mainly for the load transient. So creating load transients. So this we have discussed in week 8, which is digital voltage mode control and mixed signal current mode control. So we are not going to discuss it again. So if you want to see, you can go through SARS lecture, or you can go through our week 8 problem solving session. So now coming to the mode selection. So how the mode selection, or why the mode selection? So here the mode selection is nothing but, if you want to map it, so this thing, let me use a dark color. We can say this entire thing is like mode selection. Or I think dead time should also be coming inside mode selection. Let me check here. Dead time is also coming. So let me just quickly erase. So mode selection means from this point to this point. So this entire block is called mode selection. Whenever we are planning to write a Verilog code, so either we should draw the block diagram as well as timing diagram, then only we should start writing the Verilog code. So then we can see what exactly has to be done. If you directly start writing Verilog code, then you will not know what you are exactly trying to write. So you will not go anywhere. So first you have to draw the block diagram, the implementation, as well as the timing diagram. So then we can map your diagrams to the Verilog code and also debug if something is not working properly. So for the mode selection, so these are the inputs, and output are PWM high, PWM low, and there is one mode selection, mode detection bit, one is PWM PSL. So if we go into that Verilog code, again, the main clock 100 megahertz clock is there, followed by FPWM for switching frequency, then error voltage, then Q load, as well as Q out. I think this FPWM is not necessary because FPWM has given there. Sorry, this is FPWM PSM. So this FPWM PSM is this PWM PSM. So this we are naming it as FPWM PSM. So if it is 1, it means it is PSM. If it is 0, it means it is PWM. So FPWM PSM, then QHQL, which are the outputs. So these are the, so this is QH and this is QL. So first the input and output port declaration as well as reg. So these lines are input, output port, as well as some wires, wire and reg declaration. So it is again coming from that main function, whatever input and output ports that we have mentioned, that should be declared with the sign, if it is signed, or if it is a vector, what is the size, all these things we have discussed. And then followed by the register as well as wires that will be used in the code. Now, so we have, till now we have initialized the input, output, as well as wires and registers. Now, if we go into the code, so first let us come back here. So if we come back here, this part, what is PSM logic? So I would like to see what is my PSM logic. What is PSM logic? I'll go back and I'll see from this one. So this is PSM logic. So PSM logic is nothing but QPSM is equals to 1 if V error or V naught is less than V feedback, and 0 if V naught is greater than V feedback. So in this case, if V naught is less than V feedback, sorry, not feedback, it should be reference. You are able to follow, right? Hello. Hello.
Yes, sir, able to follow.
Okay. So V naught is less than V reference, which means error voltage is 0. And in the other case, error will be positive. So what my PSM logic does is, it will check whether my error is 0, or it will check. So here it is positive and here it is negative, because V reference minus V naught. So V reference is smaller, error is negative. Accordingly, the PSM logic has been written. So it is checking the bit, 9th bit, which is the signed bit. So if error, like if I go here, what they're doing is, if it is 1, then QPSM is 0. If it is 0, then QPSM is 1. So what they're doing is, they're checking. If I write the same thing here, QPSM is equals to 1, 0 for V error greater than 0, for V error less than 0. Okay, and when I say V error is greater than 0, which means the error voltage is positive. So the 9th bit is 0. Here error voltage is negative, which means the 9th bit is 1. So now I have written the logic. So again, the same should be written in the Verilog code. So how will I write Verilog code? I will write, if the 9th bit is 1, then QPSM is 0, else the QPSM is 1. So the same thing they have done here. So if the 9th bit is 1, which means error voltage is negative. Error voltage is negative means reference is less than V naught. So V naught is greater than V reference, and it has to be skipped. So the same thing is being happened. So here V naught is greater than V reference. So it is skip pulse. That's why it is 0. Here V naught is less than V reference and it is charge pulse. So this is the PSM logic. So with the PSM logic, what we had covered this block. Now again, the dead time block is there, as well as this AND operation is also there. So now coming to the dead time block. So this is the PWM dead time, which is again 6 D flip-flops, and each flip-flop has a delay of 10 nanoseconds. So the total delay will be 60 nanoseconds. And after getting the after delaying it, so to get the output to QH temp as well as QL temp, if I consider these two. So these we have discussed in the dead temp, how to get QH temp as well as QL temp with the dead temp. So this is including dead temp. Including dead temp. So including dead temp, what is the QH and QL? So again, this is for PWM operation. So now which block we covered? So we covered this block. So dead time block is covered, and the dead time output is QH temp as well as QL temp. Now again, one block is missing, which I mean it is yet to be written, which is the AND. So AND output is the PSM QH temp one. Input is QPSM and QPWM, and it is an AND operation. So again, this is this. So the output is Q gate PSM, and input is QPSM coming from here, and the other one is the Q out. So this is again for PSM operation. So now we got PWM high side as well as low side, and then PSM high side gate pulse information. So we got this QH temp, QH temp 1, QL temp. Now we have to use a mux, one for high side and one mux, one for low side. So how will I do? If my FPWM PSM is 1, then PWM high is QH temp 1, else QH temp, PWM high is QH temp. So the same thing has been written in a different format. So this, so these two lines are the multimode. So this is for the multimode operation. So depending upon whether my FPWM PSM is 1 or 0, depending upon that, it will be decided whether I should give PSM gate signal or PWM gate signal. So FPWM PSM. So if it is 1, then this will be given. If it is 0, then this will be given. Similarly, if it is 1, this is given. If it is 0, this is given. So this is for 1 and this is for 0. Similarly, this is for 1 and this is for 0. So these are the multimode, the two muxes that we had shown earlier. So until this point, is the concept clear? How we are defining this block, which is the new block. The rest of the blocks are again discussed in the previous session. So this is the new thing, so that I had included in my session. Okay, yeah, clear. Sir. So we had discussed that Verilog HDL. So this is the only new block that is there in the multimode. So I'm only discussing this one. So now we got QH and QL, and these are the final high side as well as low side. So these will be fed to the switches. It will go to the switches, and depending upon whether I would like to select PWM or PSM, accordingly the gate pulses will be set. And this is one important topic, so which is creating transient. So when we are operating in PWM, say when we are operating in PWM and when we are going to PSM operation, so here output current is high, and when we go step down, we had seen that the output will face an overshoot because it will take the current, because as the inductor current will not go to that value. So that extra current capacitor will take, because of which there will be an increment in the output. And then when slowly inductor current settles here, it will come back to the reference voltage. Now what happens is, if you directly turn on PSM, now the inductor current is not going 0, right? So it will not be that much faster. So V naught will come back somewhat slower. So what we can do is, instead we can allow CCM operation. CCM operation, which means if we operate in PWM operation instead of PSM for few cycles, then we can allow the inductor current to go in the negative side. And when the inductor current is going negative side, so the charge, like the discharge, additional charge of the capacitor can be discharged quickly because it is allowing the negative current, whereas here it is not allowing the negative current. So it will be taking a lot of time and there will be huge overshoot on the V0. So the same can be avoided if we go to the PWM operation and allow the current to go into the negative side for few cycles. And then so this will eventually reduce the V0 and then we can go into the PSM operation. So like this will not have that much effect on the efficiency. Like it will not degrade efficiency because these are only for few cycles, but this will improve a lot in terms of voltage undershoot, which is again like much important to the the output of that converter. Say it will again have requirement that it should not cross certain value of V0 so that V0 overshoot can be reduced. There is less than a minute, so if this meeting can quickly join so that we can continue our discussion. So again, this same thing has been discussed in all these papers. So I have embedded the link, so you can go through these papers if you need. Until this point, is it clear? So I think the meeting will end, then we can continue. If you have any doubts, you may ask.
Sir,
Yeah.
this reduction in voltage overshoot will have a bearing only on the capacitor selection, right?
It will have only a. Yeah, someone was asking the question. Please continue. Am I audible? Hello. I think Rajshekar Reddy or someone was asking a question.
Sir, yeah.
Yeah.
Sir, this reduction in voltage that we are trying to achieve, the overshoot, will have an effect only in the capacitor that we are selecting, the reduction in the cost of the capacitor.
Like not in the reduction, but like it will be much faster. Like the transient response will be much faster. Like if you see here, like the transient is ending here, so the settling time is more. So this, sorry. So if you consider this here, the settling time is more, and here the settling time is much lesser. So in terms of the dynamic performance of the converter, also it is much improving as well as the overshoot is also reduced. So like this is a better way to do. That's why we are discussing this. Like for the same capacitor. Hello.
Yes, sir, but here the capacitor requirement actually reduces, right?
Yes, yes, but like this is not the only like condition that we'll see to decide the capacitor, because this is one such transient case study, but we'll decide the or this like finalize the capacitor based on the worst case situation. So when there is a like very high step up or step down transient, then the voltage should be within certain limits, and for that to be achieved, what is the capacitor requirement? So that decides our capacitor. So provided that capacitor is decided, now if I go to that left hand side, which is method 1, and now if I go with the right hand side, which is method 2, if I do the same thing and if I see the transient response as well as the voltage overshoot, so there will be significant improvement when I operate it in the CCM operation before going into the DCM operation in terms of the settling time as well as voltage overshoot, and which can be done easily because if you do it in analog, then you have to create that logic and put the actual blocks so that it will operate in the CCM for few seconds. Whereas in the case of digital control, it just needs few lines of code, and that Sir has explained in his lectures. So this much flexibility and like better improvements we can achieve easily in the case of digital control. Is that clear?
But here, yeah, yes, but here the this DI this inductor has to be having a higher dou by dt ratings, right?
DI by dt rating
In this.
No, like inductor,
The inductor.
the slope of this will be again dependent on the V. So this will be minus V0, like M1 V0 by L. So whatever V naught that is there, so it is like M2, right? So M2 is V naught by L. So that decides this slope. So again, the amount of reduction in the V naught again depends upon the V naught at which we are operating. If the V naught is higher, then the slope will be higher and the discharge will happen faster. Again, this is a relative term, but compared to what is happening here, it will be better, like much improved response. That is what we are trying to discuss. This part is clear, right?
Yes.
Okay. Now let us go into the hardware results. So the switching frequency is not variable, sorry. So again, it is a fixed frequency operation. So it is 1.8 microhenry. These values are same. Input is 3.3 to 1 volt and 200 kilohertz, and the load step transient, and ADC 9-bit because the DPWM is 9-bit, and we have discussed that ADC resolution should be less than or equal to the DPWM resolution to avoid limit cycle oscillations. And as it is 9-bit, we are forcefully using the 9 bits of the ADC, and 10-bit we are making it 0. And the clock frequency is 100 megahertz, gain is 0.27, and these are the PID controller gains designed using the methods that were discussed in the earlier weeks. So when we consider the load transient, let us consider two load transient case studies. So in the first case, so this is the light load operation. And this is also again light load operation. So this is like full load or high load. So full load. And this is light load. This is also light load. So here it is PSM, here it is PWM, and here again it is in PSM. So what is happening? So here it is a fixed pulse followed by like charge pulse, skip pulse, charge pulse, skip pulse. I think there are two charge pulses. So these are charge pulses. And these are skip pulses. Depending upon how much it is getting charged. So it again depends upon the duty ratio. We have seen how duty ratio will affect and different types of case studies we have discussed earlier. So when it is going from PWM to PSM, we had seen that we are allowing the negative current CCM operation to reduce the overshoot. So this is the overshoot that is that we are observing when we are allowing for CCM operation. Whereas if you completely operate in PSM, right at the moment from where the step load has been applied, then the huge overshoot will be there. So this is the reduced overshoot because of allowing the negative current. And this CCM operation, that again it is in our hands how many cycles we would like to implement CCM operation, and SAR has applied it for 10 cycles. So before 10 cycles, the V naught is coming back to its initial value. So after that, it is going back to PSM operation. So for 10 cycles, it is forced to operate in PWM, and then only it is allowed to go into PSM. And this is again user choice. If we want to make it 20 cycles, or lesser cycles, 8 cycles, that can also be made. So this is the like step up and step down transient. So if you see here, it is like charging and then hitting V reference, charging again, hitting V reference, charging again, hitting V reference. Whereas here it is regulated because it is voltage mode control, and here it is based on whether V naught is greater than V reference or not. So it will be like a triangular thing. And this is the CCM operation. So if you see, this is continuous conduction mode, and this is the discontinuous conduction. Now, if we zoom in this part, so if we zoom in this part, and if we see that inductor current is actually going negative. Why? Because whenever it is operating in PSM operation, so how the voltage will be? So the voltage will be something like this. Say this is V reference. So it will charge and discharge, charge and discharge, charge and discharge. So this is V0. So if I calculate error voltage, which is V error, VE, VE is nothing but V reference minus V0, which will be less than 0. So now if I move into the voltage mode control, Kp into V error will become 0, or sorry, not 0, will be less than 0. And K derivative will be 0 because it is like previous error and present error is constant, and integrator we are resetting it to 0. So the overall control voltage will become negative, and because of which it is going in the other direction. So this can be improved by adding some feed forward term here, so that it will go in the positive direction, and it will again improve this. Instead of going in the negative direction, it can directly go into the positive direction. Have you understood the reason why it is going in the negative direction?
No, sir. Could you please repeat it once?
Yes. So in the PSM, until PSM operation, the output voltage waveform will be something like this, which will be always above V reference, because whenever it hits V reference, or it will only go slightly lesser than V reference, it will again charge, again discharge. So at this instant, if we consider error voltage, it will be, say, here it is happening negative voltage, because V0 is more than V reference, and at that instant the load is coming, and V error is V reference minus V0, and V0 is more, so V error is coming in negative. So Kp into V error will be negative. So Ncon is negative. Understood? Until this point, is it clear?
Okay.
So Ncon is coming in negative means, so it the controller is understanding that it should like discharge, because it is lesser than 0. So it is assuming that V0 should be going in the other direction, and similarly the inductor current is going in this direction. And then when it is going down, and whenever V0 is going down, then V0 is going down, V error is becoming positive, and then control voltage is becoming positive, and then it is coming back. Because until this point, it is operating in that value of V0, which is more than V reference, and because of which it is going in the other direction. So this is one issue, because it is degrading the transient performance. So how can it be improved? So one way is to provide some feed forward term here. So one way is to provide. So in this, whenever there is a low transient, one way is to provide some feed forward term, so that to make the Ncon positive, to make Ncon positive. So the same thing has been done, and sir has considered another case study. So the first one is only DPWM, so it is always in continuous conduction mode, CCM always. And the second one is multimode, so it is PWM plus PSM. And the third one is PWM plus PSM with some feed forward. Here feed forward means we are deliberately adding some, say, to Ncon, we are adding some positive term, adding a positive, say, constant, to make it positive at the instant of load step up, at the instant of load step up. So we have realized that at this instant, V error is negative, because of which Kp into V error is negative, because of which Ncon is negative. Because of the operation, it is happening like that, but it should not have happened. And again, it is hampering our transient response, because inductor current is going in the other way. So what SAR has done is, so SAR has added a positive value to make this Ncon greater than 0. So it is going in the positive direction, and again now it will improve the transient response. Is this part clear? How
Yes,
it
sir.
is being
Sir, I
improved?
have a doubt. Sir, the feed forward term is always have to be added. Can we subtract it too?
It again depends. Usually
In
in
general,
majority of the
not
cases,
exact.
it will be added on. Or
Okay, like
if you say,
how can we differentiate?
yeah, like let me give you one counter example. Say there is load step up, I naught, and there is load step down, I naught. In the case of load current feed forward, this will add, right? And this will subtract. But we are saying, say we are adding I naught information. So if it is an incremental information, we are adding the incremental information. If it is a decremental information, then we are adding the decremental information as if we are subtracting this step. So depending upon this value, either it could be adding it to the I reference or it could be subtracting to the I reference. So again, that is the thing.
Okay. Sir, and one more thing is like, though we are adding feed forward, only in the step up only, it is not showing the undershoot.
Yes.
But the other case, when we are entering the pulse skip modulation, there is an undershoot in all the three cases, right?
Yes. Yeah. So again, in the case of only continuous conduction mode, we know that when there is a step down, it will, this is the actual way of how it goes, right? So here, as if there is a peak, similarly here, there will be an undershoot because there is a second order phenomena because this is a voltage mode control, second order system. So second order system under damped. So there will be a peak for step up and there will be a valley for step down, that we know. But we have discussed here in the creating transient that if we allow the negative direction current, then the overshoot will be reduced. So for that purpose only, we are forcefully operating in CCM. So we know that it is, if it is operating in CCM, there is this kind of behavior. So until this point, we are operating in CCM. In this case also. So because that it is operating in CCM and because it is a second order underdamped system, we are getting this behavior. But when because of which the overshoot of the V naught is reduced. So after 10 cycles, then we are going into PSM. So this is happening because we are forcing it to operate in CCM. But this is happening because the error voltage is 0 and control NCON is less than 0, which we do not want. So that's why we are forcing it to be positive by adding a feed forward term. Is this part clear?
Sir, could you please make it once more, please?
Okay. So in the case of creating a transient event, so what we are doing is, if you directly allow it to operate in DCM, then through this DCM operation, the time it takes for the output capacitor to discharge this extra voltage will be huge because it is only discharging through this path. The inductor current is not going negative. So what happens is it will take a lot of time. Now what we are doing is we are allowing the inductor current to go in the negative direction. So when the inductor current is going in the negative direction, capacitor will discharge faster because capacitor is providing the charge. So it will be discharged faster, and because of which the overshoot will be reduced because capacitor is discharging faster. So we are forcefully operating in CCM operation at light load condition also for 10 cycles to reduce the voltage overshoot. So this is our aim. So coming to the same point here, if you operate in only CCM operation, it will be a digital voltage mode control, and as you know, it is a second order system under that. This is the, there will be a peak, and depending upon the integrator, there will be slight oscillations or no oscillations based on how we have designed the PI. So this is the a waveform in the second order underdamped system. So there will be this kind of peak and then settle, and when there is a step down, there will be this kind of operation. So this is coming because of the second order transfer function of the system because it is a voltage mode control. Now what we are doing is, in this case also, until this point, I am operating in CCM, and after this point, I am operating in DCM. So until this point, the waveform will look exactly similar as what it is happening in the first case. So if I consider this is case 1, this is case 2, and this is case 3. So until that point, it will be exactly similar. The inductor current waveform will be similar. So it is happening, right? It is exactly similar to what is happening in the first case. And after that, we are going into the DCM operation. So after that, this DCM operation is happening. This is for the reason we would like to reduce the voltage undershoot. So to reduce the voltage undershoot, we are forcing it to operate in the CCM. So that is the reason for this undershoot. But whereas this undershoot, this is a step up, right? So here, if you see step up, it is continuously increasing. But if you see the step up, it is happening in this way. I don't want this. And in order to not want this, so the first question that was asked is why it is coming. So the reason why it is coming is because at this instant, error voltage is negative, and because of which Ncon is negative. So because Ncon is negative, inductor current is going in the other direction because the control voltage is negative and the controller is acting in such a way the inductor current will go negative for the reason control voltage is less than 0. So if I want to go it in the positive direction, other direction, Ncon should be positive. So how can I make Ncon positive? I am adding a feed forward term so that the net negative Ncon that is coming from the controller plus the feed forward positive value that I am adding will make such that the Ncon dash is positive. So because of this, the inductor current is going in this direction. So here, the reason why it is happening is different, and the reason why here it is happening, there are two different reasons. This is happening because of the controller action and error voltage is negative. This is happening because we are forcing it to operate in CCM operation to reduce the voltage overshoot. Is this clear, Banerjee?
Yes, sir, clear.
Okay. So like this is how the transient response has been improved in the case of PWM PSM multimode digital control architecture. Now I think we'll be going into the other part. So PWM PFM. So there are two things. One is PWM PSM. The other one is PWM and PFM. So this PWM PSM, it is voltage based. So it is voltage based control, and as it is voltage based, and this is current based control. Current based control. So if it is voltage based control, we know that it is a single loop control. And we also know that if it is current based control, it is a two loop control. So we are discussing two different multimode digital control techniques, as if one is voltage mode multimode digital control, the other one is current mode multimode digital control. So in the voltage mode, it is PWM PSM, here it is PWM PFM. So here if we say PWM PSM, so in PWM, so as if it is voltage mode control, digital voltage mode control plus digital PSM control. So digital voltage mode control and digital pulse skipping modulation. Here, if you consider PWM PFM, PWM means mixed signal current mode control, and PFM means adaptive on-time control. So PFM means, as Banerjee was asking, PFM means pulse frequency modulation, which means the frequency is changing. So it is a variable frequency technique. And we had discussed in the previous session that adaptive on-time is one such technique which is used for light load conditions, because here the delta IL is fixed and it is independent of input voltage, because we are fixing the peak current, and we know that delta IL is independent of input voltage variation. So even though input voltage has some slight variations, we have seen that delta IL is fixed because we are fixing the peak current, and that's why we are going for adaptive on-time control. So this is also current mode control. This is also current mode control, and the top one is fixed frequency, and the bottom one is variable frequency, and the bottom one is for light load, and this one is for high load. Is this part clear, Banerjee? Why we are, what is
Yes, sir.
PFM, adaptive on-time? So again, the
Yes, sir.
same thing, exactly same thing. Instead of voltage mode control, we have current mode control. Exactly the same blocks, everything except the final stage where there are mux. That will be the scenario in this
Sir,
case also. Yeah.
sir, then the best of these two is like PWM or PFM, right?
Yes, like because this is current mode control, we have more flexibility. Yes.
Yes, okay, sir. Thank you.
So again, the same thing, similar to what we had discussed before. So first, we'll discuss the top-down design methodology, followed by Verilog HDL, and then followed by a few hardware results. So let us just quickly summarize the mixed signal current mode controls as I have discussed. So this is mixed signal current mode control, and again this is peak current mode control because the duty ratio is less than 0.5 for the operating conditions that we have selected. And then the light load condition is the adaptive on-time control. So this is for light load condition. So this is a buck converter, like the same buck converter that we have seen throughout the course. So this is for the mixed signal current mode control in buck converter. So we have ADC data, same thing, transient for reference or load transient, 100 megahertz main clock, Q comparator coming from this output of the comparator. Okay, and the output of is the DAC data going into the DAC compared with the inductor current generating the Q pump. Again, we have PWM high, PWM low, and then Q load for the load transient. The same thing in the adaptive on-time control also. So the overall picture remains same, except the internal blocks will be changed. So that is the only difference. But whatever blocks that we have used here, the same thing are also being used, except here the on-time is being adapted and the off-time is coming from the loop. So this is again DCM operation and variable frequency. And if we say here, the I peak is coming from loop. And here I peak is fixed because we have seen in the adaptive on-time, the peak current is fixed. So I peak is fixed, and accordingly the on-time is being adjusted. So that is happening here also. Same thing. Then if you go into the multimode digital control thing, so the same thing that we had discussed in multimode voltage mode control, the PWM PSM. So it has a single block, and again it has output or like option for multimode, whether it is PWM or PFM. Say this FPWM PFM I'm calling FPWM PFM. If it is 1, if it is 0, so for 1, what is happening? According to the code, it can be other way around also. Adaptive on time. And if it is 0, it is peak current mode control. So we can imagine again this box, this multimode digital control, this Verilog module as two different blocks inside. So this block, I can imagine as this Verilog block, I can imagine as two small blocks. So the first one being adaptive on-time control, adaptive on-time control, and the second one being peak current mode control. So if I just quickly go back to the point where we have discussed this. So it can be implemented in the same way. So this is one block and this is the other block. But there could be so many common blocks for both of them, which can be again made into a single block, and only the output will be different. So there could be so many common blocks followed by the output that mode selection that we have discussed. Same thing, we can do the same thing also. So initially to start with, we can imagine this as two different blocks. One is the adaptive on-time and the other one is the peak current mode control. But based on the similarities and the common blocks, we can club them into one block, and then we can move on to our Verilog code, and so that we can combine the common blocks and then separate out the like non-common blocks, and then at the output we have this mux. So output we have this mux thing. So again, if it is one, it is adaptive on-time. So there are two muxes again. This is a DCM operation. So for adaptive on-time, for high side, it will be the Q out coming from the Verilog code, and for low side, it is 0 because it is a DCM operation. Low side switch is always off, and the diode is conducting them throughout the thing. I mean throughout the operation. And if it is 0, FPWM PSM 0. So again, this is the FPWM PSM, which is this block. OP multimode. So FPWM PFM, now QH temp and QL temp, peak current mode control. So similar to voltage mode control, what we are getting QH temp as well as QL temp. There are two like signals. One is the high side signal and the other one is the low side signal. So the high side signal is going to 0 because FPWM PFM 0 means peak current mode control. So there are two muxes. One is for the high side and the other one is for the low side. So this is the high side mux and this is the low side mux. And depending upon the PWM PFM operation selection, either the adaptive on-time signal will be going through or the peak current mode control signal will be going through. So now if we go into the architecture, so
Sir, I have a doubt.
Yeah.
Sir, adaptive on-time, can't we include it in the voltage mode control and that pulse skip modulation in this current mode control? Like, why can't we interchange these two and implement?
Why you want to mix voltage mode control with the current mode control?
Like, how can we say that this adaptive on-time control is linked with the current mode control?
Because I have told now this is voltage based control. This is voltage mode control, PWM PSM. Here it is current mode control. So we have selected one current mode control for high load operation and one current mode control for light load operation. Here we have selected one voltage mode control for high current and one voltage mode control for low current, which is pulse skipping modulation. There is current based pulse skipping modulation as well, but as we are doing voltage mode control, so we have selected voltage based pulse skipping modulation, and you are free to select current based PSM here also, but it should be current based because we are operating current mode control throughout.
Okay. But how this adaptive on-time, is there in any like voltage based adaptive on-time control?
No, like adaptive on-time is coming because the inductor current is hitting the peak. So it is as if like this. So inductor current is hitting the peak and then becoming 0. So there is voltage based constant on-time, constant off-time, right? So that you can implement here. We have discussed voltage based constant on-time, voltage based
Yes, sir,
constant off-time.
that thing is clear, but I am not like adaptive on-time is, you are saying that it is based on the current, you are saying.
Yes.
And you are saying that adaptive on-time is not linked with the voltage at any cost.
Yes.
Okay, sir.
So like here we have selected one DPSM, but it does not have to be DPSM. It can be any voltage mode control, which has better efficiency than PWM operation at light load condition. Similarly, here adaptive on-time control is not the only control that can be selected at light load operation. Any current mode control, constant on-time, constant off-time, which has better frequency, because the main aim is to have better frequency. So anything that any current mode control or any voltage mode control in this case, any current mode control in this case, which has better light load efficiency can be selected. But here we have selected adaptive on-time because, as we have discussed this rigorously, and this is quite famous in many commercial aspects as well. So Sir has decided this because you can find the adaptive on-time in many of the commercial products, and Sir has shown few commercial product examples in lecture 118. So that's why
Sir,
Sir
like
is
it has a
selecting.
better load and line regulation too, coming to adaptive
current mode
on-time.
control. Yes.
Yes, but in case of constant on-time, it is sensitive to those.
Input voltage. So yeah, that is a very
Yes.
good point. So if you see constant on time or off time, we have seen that FSW is somehow related to V, either directly proportional or indirectly proportional, but there is a relation between this and this. And if the input voltage is changing, then the switching frequency is also changing, and which we wanted to avoid. And that's why like we have select, like, also the ripple will change. So, and that's why we do not want that, and that's why we moved on to the other like adaptive on time. So on time is adapting, so that switching frequency is more or less constant, as well as the peak remains constant. So it will not have higher peak. If say if the input is changing, if the input is more, I peak will be more. But as we are fixing the I peak, it is like fixed. Accordingly, the on time will be adjusted. Is this part clear? Hello.
Yes, sir, clear.
Okay. So yeah, that's it. Now let us go into the architecture. So in the architecture, we have V0 coming to V feedback, then going to the ADC, giving ADC data 10-bit, then the N out subtracted from N reference, giving NE. Again, the GC of Z here, it is PI controller because it is current mode control. Then we have discussed about that current reference block to put the saturation limit, also to convert from 2's complement to offset binary. And then it is going to DAC compared with the inductor current comparator, then SR flip-flop, then Q, red tail. So this is the mixed signal peak current mode control. Now coming into the adaptive on-time control. This entire part is almost the same until this point, you can say. And then here we have this comparator, and then we'll see whether it is lesser or more than reference. And based on that, it will generate a trigger signal, or you can say enable signal, going into this adaptive on modulator. And then the output Q out is coming. So now this QH temp, Q out, those are these blocks, Q out and QH temp. And now we have to write the mux code so that this PWM and PWM low, including the PWM PFM multimode digital. Again, this is not PSM, this is PFM. This small changes I will modify and then update the final PDF in the drive. So now if you go into the Verilog implementation. So the main module is like multimode MCMC. Again, it has clock DAC also this time because we are using DAC and all the input output declaration. And then here followed by, there are a few lines of code, which is input, output, say wire, and there are any register or parameters like KPK, all declaration will be done here. Then followed by module instantiation. So in the module instantiation, we have clock generator to generate FSW or FDAC, FADC, which is again common with voltage mode control and other blocks, followed by the digital PI controller. So it is again a subset of PID controller in voltage mode control, and we have also discussed this in lecture week 8. Dead time circuit, again today also we have shown quickly the dead time circuit, the 60 nanosecond dead time circuit implementation. So this is also done. Again, this modular selection is somewhat different from what we have discussed in PWM PSM. So again, we will be discussing this. There is less than a minute, so if this meeting can kindly join so that we can continue our discussion. So this is for that PWM PFM operation. So after the module instantiation, again, there are few lines of codes. So again, this is for creating transient. Which could be either load or reference. So now we'll go into the modular selection. If this meeting ends, please join me. So until this point, if you have any questions, you may ask me. Do you have any questions? Hello. Okay.
No, sir.
Okay. So, am I audible?
Yes, sir, audible.
Okay. So Shankar, PSM is not PFM. So that is what I was discussing with Banerjee. PSM is a fixed frequency control, and PFM is variable frequency control, which is pulse frequency modulation. Here it is pulse skipping modulation. So here it is based on skipping. So there is a fixed duty ratio, fixed frequency gate pulse. So either you will give that or you will just skip and give 0. So PSM is completely different from PFM. And as I have shown in today's lecture also, I have shown the PSM control architecture, and this is the adaptive on-time control architecture. And as you see, it is completely current mode, and that was voltage mode. So they are completely different because this is variable frequency, that is fixed frequency. So now if you go into that modular selection, again, we have the F clock, FPWM for fixed frequency, and then reset pulse coming from the comparator, then Q transient, FPWM PFM to decide whether it is PWM operation or PFM operation, and the minimum off time, and then Q out, which is the output of that PFM operation. Again, this is input, output, and declaration, mainly the declaration point. So this is again declaration. So this is the PWM gate signal generation, which means this thing. So if comparator is 1, then Q is 0. If S set is 1, then Q is 1. So that is what is being done here. So if it is reset, it is becoming 0. Else it is becoming 1. So this is that SR flip-flop. Okay, we have a chart. Okay, sir. So this is that SR flip-flop of the PWM. Now for PFM, what is this reset? So if you go back to this previous thing, so this is that thing. So for this adaptive on time, we need this QTR, right? So that is being coming, and then when we have discussed the adaptive on time in the previous week, I think week 10. So in week 10, we have seen there is something called adaptive on-time modulator as well as clock manager. So clock manager is to generate that enable signal, if you remember. And this is to generate that on-time, not constant on-time, the adaptive on-time followed by the off-time. So this is the adaptive on modulator, and this is the module to generate the enable. Yeah, then we have this Q out. So Q out is either QPFM or QPWM. So accordingly, it is generating that Q out signal, and then it is followed by this dead time circuit. So it is just similar to what we have discussed in PWM PSM, except there is this additional block. So these are the new things compared to PWM PSM. And these are again discussed in week 8, but I'll be only just showing what this contains, but I'll not be discussing in detail as this has been discussed in week 8. So if you go into the adaptive on modulator, so we have this adaptive on modulator. And Banerjee, you were asking that assignment and week 10 question, right? So I'll come to that question at the end of the session, but please remind me. So
Okay.
I'll discuss. So this is
Okay,
that
sir.
adapt on time. Yeah. Okay. So this is that reset that we are getting, and based on that, so I think I have shown some mistake. So this is not reset. This is the enable thing. So this is the not reset. Reset is this one. This comparator is the reset. Similarly, here also it will be having that reset, right? So this is that reset signal. So it has this block one followed by this minimum off time, because we have discussed why minimum off time is required for protection purpose, so that the system will not collapse or it will not be reaching the upper limit. So it will neither reach the upper limit nor the lower limit. So that is for the protection purpose. And this is the adapt on modulator, and the Verilog part has been discussed in week 8. Followed by the clock manager. We have seen like in order to generate this
Sir?
enable. Yeah.
Sir, I have a doubt. Sir, in
Mhm.
adaptive on time, don't we require the block where the constant on time is required?
No, on time is not constant, right? Here, what we are doing
Yeah,
is.
not, sir, not constant, but what my question is, in case of constant on time,
Hmm,
we calculate the worst case and we store it in the some register.
hmm.
But here, like, till how much time I need to on it,
Yes.
then don't we need a register to calculate and store?
No, because here whenever there is set, so inductor current is set means inductor current is rising. So until what point it will rise? Until it hits the peak, right? So whenever it hits the peak, the reset is coming, which will reset it. So the on time is this duration, and the on time is this duration. On time is this duration. So the on time is coming from the current loop rather than a fixed value. In the case of constant on time, we had a similar counter for on time also, but in the case of adaptive on time, it is not the same case, because here the on time is not fixed, only the peak is fixed, as if it is a peak current mode control. So this is, if you see, this is something similar to peak current mode control block, because adaptive on time is nothing but peak current mode control, but not fixed frequency, variable frequency, because peak is fixed, and that decides the on time, and off time is again decided by the loop. So that's why we don't have any constant on time, and on time is again not fixed. So no need to save. If the input changes, on time changes. And so here, if you see, the peak is fixed.
Yes, sir, but the minimum on time, how much time we need? Like, is it our choice or
No,
any
there
thumb
is no
rules
minimum
to
on time. Only minimum off time. So for constant on time, we
yes,
need
sir,
minimum
for
off time.
minimum off time, sorry.
So this again
Yes,
is same. This again is same. So this decides the minimum on time. So this and minimum will decide the minimum off time. So how much off time we need, that will be decided. This again,
yes, sir, like based on which this minimum off time will be decided.
yes, yeah, this will decide the minimum off time.
No, sir, my question is like how much off time we need is decided by whom?
That will be coming from the, like, see, when do we turn on this? We turn on when this output is again crossing the reference. So as if it is like something similar to what we discussed previously. So if you consider this to be V reference, so during the on time, V naught will charge, and then it will hit the V reference. And then during the on time, it will charge, and then it will hit the V reference. So whenever it is going below this V reference, that will trigger the on time. So the off time is decided by the time it takes to discharge from this V naught to V reference. So this is V naught. So the closed loop is coming, the off time is coming from this QTR, which is like a trigger signal. So in the case of adaptive on time or any variable frequency, everything is dependent upon this enable signal, because this enable signal is triggering my like on time, right? So this peak like whatever this adaptive constant on time block is doing is it will turn on for on time and it is turning off, and then who will again turn it on? This enable signal turns it on, so which is coming in this clock manager. So this, where is this clock manager? So this is like the enable generation. Understood?
Sir, no, sir, I didn't get the point. My question is like in case of constant on time, we require a minimum of 10 block, right?
Yes, yes.
Here also the minimum of 10 block has same significance as that of constant on time or not, sir?
Yes, yes, yes.
Okay. If that is the case, who gonna decide the minimum of time? The of
Minimum
the
of time
value for which the minimum value for which it has to be off is decided by someone, right?
like we are deciding it.
If-
Again, it could be like a fraction of off time. Say off time is 1 microsecond. I can choose off minimum off time to be 1/10 of the off time, say 100 nanoseconds.
Yes, is there isn't any problem? Is it user's choice? That's it.
Yes, 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 yes. It is completely user choice.
Okay, sir. Thank you.
So that is all about this adaptive on time modulator. Now, if we come back to our initial thing, which is clock manager, we have seen for generating this enable, which will trigger the adaptive on time modulator. Adaptive on time modulator. So this clock manager, again, we have discussed this. So this is the block, and these are the edge detect. So for edge detect, what is the logic also we have discussed in the previous session, followed by this block. So these are the declaration, and this is the wire declaration. What are the wires that are needed? And this is the AND operation. So these are the AND operations, followed by the edge detect, and this is the final OR operation. So this is the clock manager. Again, this we have discussed in weekend, so I will not be again spending time on this. So this completes that PWM PFM operation. So just to summarize, at light load, it is operating in adaptive on time, where the on time is adapted as the peak is fixed. So input voltage variation will not affect the ripple. Instead, it will change the on time so that the ripple remains constant, and off time is coming from the loop. And at high load conditions, it is operating in peak current mode control as the duty ratio is less than 1. So for this case, input voltage is considered to be 3.3 and V reference is considered to be 1 to 1.4. And switching frequency in PWM operation, it is 200 kilohertz, whereas in the case of adaptive on time, it is variable. And these are the gains that are considered, and these are designed using the methods that were discussed in the earlier weeks. So if we consider the load transient, so this is only PWM. So at light load also, we are operating in the PWM operation, and this is PFM operation. So again, the same things that we had discussed in the PWM PSM is happening. So the first case is current is going in the negative direction because V error is less than 0, and because of which Kp into V error is less than 0, because of which Ncon is less than 0. That is one thing. And if we consider here, again, we are allowing 10 cycles of CCM operation. To reduce V naught overshoot. So the same thing, we are again, we have the flexibility to choose the number of cycles for which we would like to operate it in the CCM operation. So this is the same thing. So this is a different happening for a different reason, and this is happening for a different reason. This we are forcefully making it to operate in such a way so that the output overshoot will be reduced, and this is happening because the error is negative, and because of which Ncon is becoming negative. But if again we want it to be faster, then we can add load feed forward. That can be done, but I don't think Saresh shown for this case study, but it can be done. So this completes our PWM PFM operation. Now we'll go into the bi-frequency DPWM. So bi-frequency DPWM, we are, as the name
Sir, I have a
suggests.
question.
Yeah.
Sir, like there is a thing like a VM in voltage mode control, it behaves as a second order circuit, and current mode control behaves as a first order. What's the thing behind it, sir? I'm unable to
Like if you consider
go.
that loop transfer function, K loop, like say for continuous time only you consider K loop of S, it will be GVC or GVD of S in the voltage mode control into GC of S, right? In VMC, excluding the other gains. So it will be like a second order. And not
In
actually
case
K
of
loop, it is
yes,
actually
yes,
the
sir. I got
output
some
to
point right.
uh-huh.
Like in case of current mode control, we just use PI.
Yes. So this is the
Whereas
closed loop
in
transfer function. If you consider that K loop by K loop of S, or so closed loop transfer function in voltage mode control is second order. And in the case of current mode control, it is first order. So because of that, here it is behaving like a second order, and here it is behaving like a first order. That is the
like
reason
which
behind
is
it.
better thing, sir? Like first order
It
being
depends
first
upon
order is
your requirement. See, if you have a current requirement, then see voltage mode control, what it does, it will only regulate the output voltage, and current, it is not in your hands. If the current is exceeding say 10 amperes, you cannot force it to operate less than 10 amperes. Whereas in the case of current mode control, we have the flexibility to put in like peak saturation limit. So here we have the flexibility of operating or controlling two things, voltage as well as current. So we can have more flexibility, more degrees of freedom. So current mode control, it has much flexibility.
okay.
But again, it depends upon
Okay.
the application, where if they are having no such stringent requirements on the current, and if they're operating in voltage mode control, it is again the application as well as user choice, whichever control is like best suitable for that application, that control technique should be used or selected.
Okay, sir. Thank you.
Okay. So that is this. And in bi-frequency DPWM, you can say this is like a voltage mode control. But in voltage mode control, we have switching frequency 1. In the case of bi-frequency DPWM, we have two switching frequencies, which is FSW1, FSW2. We'll go into that in detail in the upcoming slides. So the same thing, we'll first start with the design methodology, followed by Verilog HDL, and then the hardware results. And then after this, we'll solve few problems. So bi-frequency DPWM, again, it is a current mode control, voltage mode control, as I have said, except in the voltage mode control, the counter has single frequency. Here it has two frequency. So until this point, it is same as the voltage mode control, PID controller. Now it has a bi-frequency option, whether you want the bi-frequency or you do not want the bi-frequency. Again, according to 1 or 0, if it is a 1, then bi-frequency it will be operating. So it has two frequencies, FSW1 and FSW2. If it is 0, it will only operate in the switching frequency FSW. And this is the control voltage VC of N. And it has DPWM, counter-based DPWM. Yeah. And then the output is again going into the dead time, same as voltage mode control. So this again is same as the voltage mode control, except here we have this additional option, whether we'd like to operate it in the bi-frequency operation or not. Then followed by output are PWM high, PWM low, and then Q load for the load transient. Here Q trend to select whether it is a reference transient or load transient, and the main 100 megahertz clock. And here we have ADC and the FADC coming from the Verilog module. So if we go into the architecture wise. So this is the control voltage generation, right? V0 with a feedback gain, then the digitized output voltage subtracted from the end reference to give an error voltage, then followed by the control voltage. So now this control voltage is compared with the RAM. So in the case of bifrequency, again this ncon is getting resized because we want it to be certain number of bits, and we have discussed in the voltage mode control how to discard the least significant bits and all those things. That is generating this reset pulse. So when we say bifrequency, so this PWM, FPWM, right? If it is a single frequency, then FPWM is say 200 kilohertz. But if I want it to be operating at two different frequencies, then FPWM should be changed. So accordingly, my QPWM will also be changed. Say in one cycle, I will operate at 210 kilohertz. The other cycle, I will operate at 190 kilohertz. So the net will be 200 kilohertz, but I'm continuously shifting between two different frequency of operation. So that is what is being happened here, or that is what we are trying to do. And this is the block that we have discussed in the previous version. So this is the how bifrequency operation is happening. So yeah, this is what we are saying. So FPWM itself is having two different frequencies. So in the first cycle, you say it has FSW1, and in the second cycle it has FSW2, and in the third cycle it has FSW1. In the fourth cycle it has FSW2. And if you do the average, say it has the frequency FSW 200 kilohertz. So one thing we can say, FSW1 is FSW plus delta FSW, and FSW2 is FSW minus delta FSW. So I'll come to the reason why we are adding and subtracting. That we'll discuss, but this is the operation. So one thing is, in each and every cycle, I can change. So it could be something like this: FSW1, FSW2, FSW1, FSW2, up to so on, FSW1, FSW2. So this is one way of doing it. The other way, or best way, could be operating in FSW1, FSW1, up to so on, FSW1 for 10 cycles, and FSW2, FSW2 up to so on, FSW2 for 10 cycles. So in the previous case, we are operating one each. In this case, we are operating in 10 cycles each or 20 cycles each, whatever SAR has selected. I'm not sure. I think SAR might have selected 10 cycles each or 20 cycles each. I don't remember that. So SAR is operating at 10 cycles in one frequency, and at in the 10 cycles in the other frequency. So now if we coming again, SAR has a paper on this bifrequency DPWM. So if you are interested, you can go through this lecture. I mean, paper and IEEE paper. But it is not mandatory. It's up to your interest. If you're interested, you're free to go through. Then if we come to the Verilog implementation. So voltage mode bifrequency DPWM, and here the declaration. And what exactly is the change in comparison to the conventional voltage mode control? Only the switching frequency or only the FPWM is changed. So rest of the things are exactly same. Only the PWM is being changed. So the entire thing is same. So here also this is creating load or reference transient. So this is the creating transient event. So just similar to voltage mode control, it has a clock generator, it has a digital PID controller, and it has a DPWM type circuit also. Only change will be this part, FSW, FPWM. So in the case of normal digital voltage mode control, we have only single FSW. Here we have FSW1, which is FSW pi plus delta FSW for 10 cycles, and FSW2 which is FSW minus delta FSW for 10 cycles. So we are operating at two different frequencies, but if we take the average, then we will get FSW, which is our 200 kilohertz. Okay, so until this point, is it clear? Like the logic, the reason for this logic, we'll get into that in the next slide, but the logic and how it is being implemented, how it is different. Yeah.
Sir, could you please like how it was evolved, sir? Before you said in the before slide you said for one cycle or one frequency for one cycle and one frequency for 10 cycles. This thing
Yes.
is clear. Before this,
So like
the slide before this,
this one.
oh yes, sir.
Okay. Yeah, what is your doubt?
Yes, like how this frequency by frequency is coming, sir.
So
We have to
this part FPWM, if it is 200 kilohertz, then it is a fixed frequency. But if FPWM has two components, FSW1, FSW2, so then this bifrequency thing is coming.
okay. Okay, you are including this two frequencies in the FPWM itself.
FPWM itself, yes.
Okay, sir. Okay.
And why we are doing that, we'll get into that. So it's, if it is a fixed frequency, we'll have this, right? So this is fixed frequency. But if you consider two different frequencies, so in one case, it will have more time period. In the other case, it will have less time period. In one case, it will have more time period. In the other case, it will have less time period. But the average, if you consider, so this is T1 and this is T2. But if you consider T1 plus T2 by 2, it will be T, because over a certain number of cycles, we are trying to maintain the same average switching frequency, but individually it is not same. So either you can do in each cycle, you can change FSW1 to 1 to 1 to, or you can keep 1 for 10 cycles or 2 for 10 cycles. So if you take an average of 20 cycles, the switching frequency average will be again 200 kilohertz. So average is 200 kilohertz, but not in each switching cycle. So the reason we'll get when we see the hardware results. So the same KPK, KD, like for voltage mode control, how we are designing, the same thing we are designing, except there is slight change in the switching frequency. So the other things, everything will be the same as voltage mode control. So now coming into the main thing. So let me change the color. So this is fixed frequency. So it has 200 kilohertz. And this is bifrequency, which means average is 200 kilohertz, but we have not used 200 kilohertz switching frequency. Instead, we are using 200 kilohertz plus some delta, 200 kilohertz minus delta. And if you see this some oscillations, maybe not that much noticeable, but in the oscilloscope, we can see that it has different frequencies, and that delta FSW, I'm not sure exactly. I think SAR is considering either 2% or 5%. I'm not sure, but I think mostly 2%. So SAR is considering 2% T. So the time period T1 is 1.02 T and the time period T2 is 0.98 T. So something like that SAR is considering. I'm not exactly sure about the percentage, but it is plus a fraction of delta T. So now if you consider here, so this is the FFT, right? So this is the FFT, which will give the what can I say, the harmonics and the frequency components. And this is the FFT for by frequency. So if you consider here, so this is 200 kilohertz. And this is 400 kilohertz, sorry. So this is 400 kilohertz. And this is 600 kilohertz. So the harmonics are getting smaller and smaller, as we know. And yeah, but there is a peak at 200 kilohertz, but because we are operating at fixed frequency 200 kilohertz. Whereas in this case, we are not operating exactly at 200 case, but we are operating slightly lesser frequency as well as higher frequency, but the average is 200 kilohertz. So if you see this peak is getting spreaded, that's why it is called spread spectrum. spread spectrum, because the frequency is being divided, so the peak is also getting reduced. So peak is reduced compared to the fixed frequency DPWM. So the main intention is to distribute the spreads like the FFT. So here it is getting distributed. So that's why it is called spread spectrum. And how we are doing that, instead of having a single frequency component, we are adding two different frequency components. So the single frequency component will be reduced and it will be distributed. As you can see here, there is a sharp peak. Here it is being distributed because it has the other, not exactly this peak, but average, since it has that peak. So the peak is getting distributed. Also, there is no such sharp edge. Instead, it is actually getting distributed over wide frequency range. So that is the advantage of this. And you may please go through this SARS paper also if you have some more interest, like if you have interested, if you want to know more, then you can go to this paper. But yeah, this is the basic thing. So that's why we are using two different frequencies, and we are actually spreading the spectrum, and it will cause slightly in the transient response. If you see there, it is 1, 2 oscillations, and third oscillation is not that much. But if you see here, there is some increment in the oscillation. So there is slight change in the transient response, but not that much noticeable difference, but it is still okay, because here the frequency of operation is different. So there might be slight effect on the transient response, but not as such severe or drastic effect or like degradation of the transient performance, but it is almost same, except there is slight difference on the transient response. So until this point, is it clear?
So like the peak is reduced and spectrum is spreaded.
Yes.
Up to that I'm clear.
Okay. Okay. What is your doubt?
Sir,
Like
this
okay. Continue.
Okay. Yeah. One of you can ask, so other can ask. Yeah, Banerjee, please continue.
Okay, sir. That's the thing.
Okay. You don't have any doubt?
No, sir.
Okay. Yeah. Rashekar Reddy, you're asking something?
this case we have done for that one delta FS1, that is sorry, FS1 for one cycle and FS2 for the next cycle.
Yes.
This is that is the case we are showing this FOP.
Yes.
Sir, if we similarly that the case you have said 10 cycles for one frequency and next 10 cycles is 100 frequency, then at that time what will be the FFT change, sir? Because
yes, this is the FFT for that case, for 10 cycles of FSW1 and 10 cycles of FSW2. Say SAR has considered here how many cycles? 20 cycles. SAR has considered here 20 cycles, because this is 40 microsecond and each cycle is 2 microsecond. So SAR has considered 20 cycles, which means SAR has considered 10 FSW1 and 10 FSW2, which is again similar to considering 10 individual FSW1, FSW2. So SAR has considered one complete set, so it has equal amount of FSW1 and equal amount of FSW2. So the spectrum will see FSW1 component as well as FSW component, which are equal in number, so it will be equally spread. Even if you do FSW1, FSW2, FSW1, FSW2, it will still be the same, because over 20 cycles it is getting average out, and the average is 20 kilohertz, 200 kilohertz, so it will still be the same.
then, sir, what is the maximum delta FSW we can go?
Again,
yes.
So if you increase again more delta F, then this effect will be increased. So the controller for which, like the controller which you have designed for 200 kilohertz may not be exactly giving you the expected transient response for the other case. So this effect will significantly improve. So if you increase that change in the switching frequency also, say here it is operating like this, and if the increment is negligible, then there is no transient. But if the increment is huge, then it might undergo a transient and then it might come back because the increment in the switching frequency is huge. But if you see here, the increment is so less that it is as if it is having no transient. But if you give say huge difference in the switching frequency, then after this instant, like after this instant, it might have to go some transient, like say 1 or 2 cycles, so that it will again come back to steady state, which is again not desirable. So again, that we should keep in mind. Also, the effect it is having on the transient response, that should also be kept in mind. Is that clear?
Yes.
So with this, we complete our session. So we have briefly discussed first one, the voltage-based multimode digital control, which is PWM/PSM. And in the second, we have considered the current mode control-based multimode digital control, which is PWM/PFM. And in the third part, we have discussed about the bi-frequency DPWM. Okay, now let us solve a few problems. Again, if you clearly understand all these things, then you will be able to solve. But I have given a few problems based on like which will test your understanding about the concept. So the first problem goes like this: consider a buck converter operating under voltage-based bi-frequency DPWM. Let me change the color. Voltage mode bi-frequency DPWM using an FPGA with 100 megahertz clock. Now, what I'm trying to say is, if the switching frequency is generated using a counter-based DPWM and it counts till 509 in 10 cycles and 489 in the other cycles, what are the FSW1 and FSW? And we know in a counter-based DPWM, if it is counting from 0 to NR minus 1, we know that F clock is FS, not FS. It is the other way. So F clock or FSW is nothing but F clock by, it's a fraction, right, by NR. So the same thing. So T clock by TSC is 1 by NR, which means FSW is F clock by NR. Isn't it? Yeah. Yeah. So T clock is TS by NR. So FSW is F clock by NR. Yeah. Now, what they are saying is what are FSW1 and what are FSW2. So if I take FSW1, so what is FSW1? FSW1 is 100 megahertz by, what is NR? Can anyone say? Hello.
509.
Yeah, but NR minus 1 is 509. So NR is 510 because we are counting from 0. So it will be 510. And similarly, what is FSW2? Let me use a different color. So FSW2 is 100 megahertz by 490. Yeah. So these are FSW1 and FSW2. So that is all about the bi-frequency, the first problem. Now, if I go into the second problem, so I have given a buck converter, consider a buck converter operating under PWM PFM. Write the Verilog code for the gate signal generation block as shown. So I wanted you to write the Verilog code for this, provided Q out, QH temp, QL temp are given, and PWM PFM are also given. Like no need to do the input output declaration, just we have to write the Verilog code. So how we will be writing? So can anyone tell me how to write the Verilog code?
There will be a conditional statement.
Okay. Yeah.
For PWM, if
again, there is less than a minute,
PFWM
so if this meeting can quickly join, so we can
question mark
continue.
is Q out.
Yes.
So this first one is PWM question mark colon Q out colon.
Yeah, yes, you're getting it, but syntax should be correct. So there are again two ways. So first, I'll tell you in method 1, which is a simpler way. I think this meeting we will end, so quickly join so we can discuss this question. So PWM high is equals to, say this is FPWM PSM, FPWM PFM. Hello. So it is F underscore. Am I audible? Can someone please confirm? PFM question mark.
Yes,
And
sir,
if it is-
audible.
Okay. If it is 1, it will be Q out. Else it will be QH temp. Similarly, PWM low, which is F PWM PFM, and question mark whether it is Q out. So for adaptive on time it is 0, and for the other one is QL temp. So this is the way that we have discussed. So semicolon semicolon. The other one is the method 2. So in the method 2, I can write something like this: if F underscore PWM underscore PFM. So if it is 1, then I will write SN, or depending upon, say if it is wire, then I will write SN. If it is not wire, then I will write SN PWM equal to I. So again, there should be SN here. Here also SN. So the same thing if we do here. So we'll have SN. There will be begin end because there are multiple. SN PWM high is equals to Q out, and SN PWM low is equals to 0, because it is 1 means it is adaptive on time, and then if condition is ended. Now the other part, which is else. So else, now we will do the PWM part again. So begin assign PWM high is equals to QH temp semicolon, and for the low side assign PWM low is equals to QL temp semicolon else. And so this is one way, which is a much simpler way, as you have seen, and this is easy for us to implement, but like code lines will be more. But in both the case, the compiler will treat them as the same thing because it is the same logic, and it will eventually lead to the same building block. But it is just user's choice, whichever way he or she is comfortable with, then that method can be used. So till this point, I hope it is clear.
Yeah.
Okay. So just let me summarize before we go into the doubt Banerjee has asked. Let me just quickly summarize. So today's session is about multimode. Okay, let it. I think it will take some time to come out. Okay. Okay. So today it is all about the implementation of multimode digital control. And this could be again two things. One is voltage mode control, and one is current mode control. And in the voltage mode control, we have discussed PWM PSM. And in the current mode control, we have discussed PWM PSM. And in PWM PSM, here it is digital voltage mode control plus digital pulse skipping modulation. Here it is peak current mode control plus adaptive on time. And bifrequency is independent of the digital control. So in both the cases, we can apply wherever there is fixed frequency, we can apply the bifrequency. So bifrequency DPWM, which what I mean to say is here there will be a fixed frequency clock. Here also there will be fixed frequency clock, and here also there will be fixed frequency clock. So instead of that fixed frequency clock, we can keep 10 cycles one fixed frequency, 10 cycles the other fixed frequency, and we can implement bifrequency DPWM. Here it is a variable frequency because and there is no question of bifrequency because it is not in our hands, it is coming from the loop. So that is all about the summary. And there will be another 1 hour session and day after tomorrow, 18th October, Wednesday, from 6 p.m. to 7 p.m., where I will be mostly summarizing what we have discussed and followed by few problems if time permits. So there is, and Banerjee has asked one question, and which is from assignment 10. I don't remember which question. So one of the question, which is again based on either adaptive on time or constant on time control. So I will not explain the exact answer, Banerjee, but I will give you a hint which using which you will be able to solve. So there is this set, there is this reset, there is this queue. So now I would like to draw the set. I think so this is set.
Sir, excuse me.
Yes.
Sir, the thing that is from which I am suffering is what are the initial conditions I have to choose before going to analyze that thing, sir?
This thing.
Not only this thing, in that problem, this is the difficulty I am facing.
What is the difficulty?
Like for reset, I have to think it is a 1 or 0 or like that thing.
I mean, I'm not following.
Like there are two SR flip-flops, right, sir?
Yes.
For whether I have to take the reset to be 1 or 0 when I am starting to analyze that circuit. The initial conditions I am unable to pick up.
So you can always start like, so let me say, so you can say at t equals to 0. This is t and this is also t. So you can consider at t equals to 0, there is a set pulse. And then it is like this. So this is set pulse and say this is reset pulse and this is Q. So this is set and say this is reset. So now what will be the Q? Q will be something like this. Isn't it? Do you agree?
Yes, sir.
Okay.
Yes, sir, I agree with you.
Yeah. Now there is slight modification and I'll draw something like this. Okay. I need more space. So I'll draw something below that. So so this is my set, this is my reset, this is my Q. And what I'm doing now is I'll give set pulse to reset and reset pulse to set. And let me check what will happen. So I'm giving here the reset pulse and here I'm giving the set pulse. Okay. And I'll see how my Q will be coming. So let me just check quickly that. This is T and this is the reset and this is the Q and this will be the final thing which will come. So again, this is my set S, this is my reset R. So this S and R are this. Okay, and this is my Q. So set pulse has, so for the set, I am giving the reset signal. Okay, so which means I will give set here and rest of the part it is 0, which is the same. Okay, now coming to the reset. Reset, I am giving the set pulse. So this is my reset and this is my reset. Okay, again, This is same as this. So now what will be my queue? My queue will be something like this. So at reset, it will be reset, and at set, it will be set. So my this one will be this, and this one will be this, isn't it?
Yes, sir.
Okay. Just imagine I put a NOT gate here and say this is Q dash. And in such case, what will be my Q dash? My Q dash will be something like this, isn't it?
Yes.
Which is same as this. Which means these two are same. Do you agree?
Yes, sir, agree with you.
Yeah. Now you check option 5, and then you will be able to know. So this is the only difference. So in whatever question Banerjee was asking, if you can say, it will be helpful to others. So it is in assignment 10. So there are two options that
but-
are read. This is option 2 and this is option 5.
Oh,
You just check. So this is the logic. If you are still confused, I would recommend you to draw it, hand draw it, and check the gate pulses. It will be the same pulse. Only we are setting and then we are resetting it, but it will still be the same. But just give it a try. So this is the logic behind that, and then you will be able to see. So only there are 2 flip-flops, I think. So the 2 flip-flops have been changed accordingly so that it would still remain the same.
okay, sir. Sure, I will check it.
So I hope you are able to follow this session and you are able to understand the concepts. So this is our last week technical session, and next week it will be more of a summary and few problem solving session. So yeah, I'm looking forward to seeing you in the next session on Wednesday, 6 to 7 p.m. Hope you are free that day. If you do not have any more further questions, we can end this session here.
Sir,
Thank
like I have
Yeah,
a
the
question.
link may be coming on tomorrow, sir.
Sir, sorry.
The link may be coming on tomorrow, or
Mostly, even if
Yeah,
you do not
okay.
get the mail, you have the same link, right? Zoom link. So even if they forgot to inform you, just join in the same link, like whatever link we are using. So I'll be there from 6 p.m. to
Today's
7 p.m. Yeah, the same link. Like you are using the same link throughout the weeks, right? So the same link, you can just click it and you will be coming into this meeting. So I'll be there.
No. Sir, we are sending different links every week.
They're sending different links. No, I think the mail they're sending different, but it is the same link.
Okay.
Like from my side,
Okay.
I have given them one Zoom meeting link, which they'll mail you each and every
Okay.
week. So I'll be joining the same like Zoom link, but you will be directly clicking that link. So if they forgot to send you, I'll remind them. But if you do not get any such mail, you just join the same link. It's a week 12 session. You go to that mail and join that link.
If there is any change, you will update in the forums
Forum meaning?
or doubt or group.
No, like let me see. I hope like today I got a mail from them that they'll be circulating the Zoom meeting, but if they fail to do so,
Okay, sir.
I'll contact them or I myself send the link to all of you. Okay. So if you have no more queries, then I'm ending this session. Okay. No, sir, same link. Yeah, it is same link. So Shankar has confirmed it is the same link. So you can join the same link. Okay.
Hello,
With that,
hello.
yeah.
Sir, like in the session where we went through this, we are extending for 10 cycles the PWM, right? Sir, before that, you are saying that there will be second order.
Sorry, can you
Second
please
order
repeat?
response. In the PSM or PFM, PWM or we are extending the PWM for 10 more cycles, right?
Yes, exactly.
In that case, in the first diagram you have shown, you are saying that it will have second order response.
Yes.
Like, is that the same case with the current mode control and the voltage mode control also?
Yes, like almost the current waveform is same. So that's why there is a dip for the 10 cycles. And after that, it is going to PSM in voltage mode control, and it is going to adapt to on time in the PFM control. So that is why there is that dip coming in the inductor current, right? Because that is because we are operating in PWM for 10 more cycles. So that is why it is coming like.
But one is current mode control and one is voltage mode control, right?
Yes, yes.
Voltage mode control will be second order.
Actually, the voltage mode control second order is the output to, like, it is the V naught. So if you see the V naught waveform, it will be the second order, but current waveform, it depends upon what value of PI controller we have chosen. So when we say the second order, it is the voltage.
Okay.
Yeah. So second order, in the case of voltage mode control and current mode control, it is strictly first order. So in V naught, you cannot find that undershoot and then overshoot. So current is different. We are not talking about current. Current can be like it will have that peak as well as some few oscillations in current mode control as well. But we are talking about voltage mode control first order. So when we say the second order and first order, it is the voltage, not the voltage waveform in the case of voltage mode control, and as well as the voltage waveform in the case of current mode control. So if you see alternative method, you can see that voltage is having a second order behavior, whereas in the case of any current mode control, you will not find that because of the transfer function. So that is the voltage undershoot as well as overshoot. And if you take the current response, depending upon its order, that waveform. So I think it is, you should check what order of the transfer function you are getting for current mode, like the current transfer function. Is that clear?
Sir, clear. Thank
Okay.
you.
Okay. Okay, then see you on Wednesday. Have a good day. Good night.
Thank you.